So you wanted 18.50 here.
Yeah, 18.05, 18.20, and 18.30.
Okay, right. Right then, so finding the number, how much is n? Okay, which is our first, second, third, and the fourth question was to find the uncertainty, which we did. Why do we times it by twice when we are finding the uncertainty? Because we are using the burette twice. Okay, the reading is taken by using it twice. All those things are
Yeah.
discussed now. We are at the fourth or the C part, I guess. Okay, C part, which is about finding the n, the number of carbons and hydrogens, okay, according to the equation, which means discussion. So since we need the data, I'll remain in the previous page and explain you. Hope you have the printed paper so you can look at that, right?
Yep.
So back to the question of finding the n, which is very interesting, as I said to you. First, let's find out the amount of sodium hydroxide used. Okay, the amount of sodium hydroxide used in the titration. So we are starting the
Yeah.
question here, remember here. Okay, so finding the number of moles, it will be an NaOH that is found through C times V, concentration times volume, and the concentration is?
The concentration is 0.24.
Yes, 0.240 mole per dm cube times the volume used. Now we had found that as well. That was here, right? Third one. How much was it? We took only these two results into
18.25.
account. Exactly. Why do we take only these two?
Because the other ones could be like anomalies. Hello?
Yes, that's right. 1 second. How much is the value here?
Sorry, where?
What's the value? What's the amount if we solve this? And where comes that 10 to the power minus 3?
Oh, I got 4.38 times by 10 to the power minus 3.
Exactly, that's right. And that will be straight away the moles. Why do we write 10 to the power minus 3 for the conversion, right? Because we had our concentration in mole per dm cube, but the volume that we found here was in centimeter cube. So the conversion is very important. And we did that. According to that, what will be the amount that of the dioic acid that we use in this titration?
So you have to divide it by 2 because
Exactly. Reason
the
is?
ratio,
Yep.
the ratio on the equation.
Exactly. So this is 2, this is 1. We are looking at the
Yeah.
coefficient in front to compare the ratio, the mole amount, the amount ratio. So that is going to give us 2.19 times
Yep.
10 to the power minus 3 moles. Okay. Now the question, to find the amount. That is this. And do you remember that is the amount present on 25 centimeter cube? Because though we prepared 250 centimeter cube, we were transferring only 25 centimeter cube into the titration class to do this,
Yeah.
right? So if it is the amount on 25 centimeter cube by the volume, what will be the amount on 250 centimeter cube? It's going to be simply 10 to the power, how much?
Minus 2.
Minus 2 moles. Okay. Now come back to the very basic equation that we have studied, that is to connect the amount with mass and molar mass. But how did I decide that I have to go through this equation next? Because I know now I have made use of this, I have made use of this. I'm thinking of making use of this data. Since it's mass, the first equation that strikes in my mind is N equal M over MR, mass over molar mass, right?
Yeah.
So by the time that you're starting doing this question, you won't have 100% idea. Okay? It's the same
Yeah.
to me. So we have to just start so that it will lead us with the next step. Okay, the mass here is known. The amount here is known, but not the molar mass. So let's find out that molar mass. Hence, the molar mass will be m over n, and the mass here is 2.891 grams. Amount is, let's say this. So how much do you get for the molar mass?
For the molar mass, I got 132.2831.
132.009. So let's keep it as 132 grams per mole. Now coming back to the dioic acid. Okay, but we have finally found is the molar mass of this dioic acid. And we have to understand that molar mass can be gotten if we add up all the elements present. So along the dioic acid, which means two C double bond O OH groups, we have two of them, right?
Yeah.
Their mass alone will be 60. Am I right? Did I do that correct? Can you double check?
I think it's 90.
Oh yeah, because we have two hydrogens. So, sorry, two oxygens I meant, plus one hydrogen, plus a carbon. So times it by 2, we get 90. Thank you for double checking that on my behalf. So 90 grams per mole. Now, 132 minus 90 is going to be 42 grams per mole. That is made up of that CH2 times N.
I
And
think what I
CH2.
got confused with was that I thought that N also was like the number, like I thought you had to calculate the value of N and that it was also including the first like carboxylic acid group.
It doesn't have to, because in the formula, they have clearly given that N just next to the bracket where CH2 is. So that N is the number, the count of how many CH2 groups we have. So finally, the rest is just the calculation, mathematical calculation. That's all your calculators work. So let's not worry about that. And it's a 3. Now, which means this dioic acid should have had 3 actually, 3 CH2 groups in between. And this is how it should have looked, right? Okay, I have done a deliberate mistake and I was waiting for you to correct me on drawing this structure. What do you think I have done wrong? Simple, yet we have chances to lose the marks. This hydrogen
You've
is
drawn a
unnecessary.
double, yeah.
Yep. That makes the carbon having excess bonds. Carbon can only occupy 4 by maximum bonds. So this is all good. And this is how the real structure should have been, right?
Yeah.
Okay, now, regardless of this mathematical calculation, let's say I have given you an unknown compound. It can be an acid. Let's say it's a carboxylic acid, not even dioic acid, it's a carboxylic acid. But we do not know if it is methanoic acid, ethanoic, propanoic, butanoic, pentanoic, or hexanoic. We do not know. And I'm asking you to find out its formula. So, what will be the quantitative analysis method that you will be doing to do that? Imagine you are in my laboratory and I'm asking you to find out the molecular formula that of a known carboxylic acid. I mean, the functional group is known, which is carboxylic acid. You are supposed to find out the real number of carbons and hydrogens on it. So what's the quantitative method?
Do you like use the mass spectrometer to find the molecular formula and then like maybe the IR interoscopy?
Exactly, mass spectro can be used, which is very good. I appreciate that idea. IR is unnecessary because IR, we mainly use that to find the functional group. Do you remember?
Oh yeah.
using the broad peak and then the CH3 group peak, the broad peak that on this range is OH, all those things. That is for the functional group mainly. So mass spectrometry is a good idea. That's a very good idea. Now let's say I wanted you to do a titration. I made it specific, saying that please do a titration and then find it out. So what do you think you will be doing? What are your steps?
For the titration,
Yes, I want you to carry out a titration and find it out because it's an acid. So what titration specifically? An acid-base titration. You can think of one which is acid-base titration. And what are your steps?
um, first you have to make a standard solution,
Very good. What do we
and
mean by that?
so it will be like 25 centimeters cubed of like the particular like concentration in the flask. I mean, I
Mhm.
think you have to,
Yeah, making a standard solution is a known mass dissolved on a known volume, right?
yeah, yeah.
Okay, so let's say you wanted to measure 3 gram, okay, something like that, and you wanted to dissolve that on 250 centimeter cube water. So do we just measure it using the weighing scale and then transfer that into the beaker and then dissolve it when it comes to the
Y-
experiment, the practical? Are you
Uh, y-
repeating the practical skills as well?
Sorry?
Are you going to repeat the practicals?
Yeah, I think we still have some more practicals to complete.
Okay. All right, now tell me how to prepare a standard solution. Idea is measuring a known mass, dissolving that on a known volume. What instruments to be used? What steps to be followed?
So you would need a volumetric pipette, I think.
Mm-hmm.
Uh, and well, I mean, first you probably have to weigh the like solute with the balance,
Mm-hmm.
maybe up to 3 digits, and then you put it in the beaker, and then you dissolve it
Mm-hmm.
with water,
Mm-hmm.
and then you measure the volume of the solution,
Mm-hmm.
and then well, you have to stir it to dissolve it, I
Mm-hmm.
think. And then you,
Yes.
um, I think, is this where you transfer it? You transfer 25 centimeters cube into a beaker.
Okay, right. I'll help you with that using the picture. Maybe you referred to the picture saying that this way, right?
I was just trying to remember what I did in class.
Okay, I'll help you further with that. Before that, let's revise what we did mathematically here on finding the amount. So where we started is we just started at a point. You know, you don't have to necessarily start here. But then why did I start there? Because I know titration is every time comparing the amount. We can find an unknown amount by the known amount. So I know what is known here by the amount what is known here because the concentration that of NaOH is given and the value that from the table we found for the mean titrate is 18.25. So that's the volume of sodium hydroxide. I wanted to start there. I found the amount. That gave me the next lead. Since I know this amount, I can compare this using the ratio by the coefficient. The coefficient here is 1 to 2, an unwritten 1 and a written 2 that is representing 1 mole of this dioic acid will require 2 mole of NaOH. So if this is this, half of that is the amount of dioic acid. But that is of 25 centimeter cube, which means when it comes to 250, where comes that from? That is the original volume. It will be 10 times of that moles, which is this. Since we know the amount, Okay, I was not sure how to do next, but then I noticed that we made use of this data, but then this was still remaining, and that is about mass. So the equation that just came to my mind is this, and that's where I started. So M is known, N is we have found it so known, MR is missing. Then I thought of finding the MR, and that was this. But about the MR, we know we can normally find it if we know the molecular formula by adding up the mass numbers of each of the elements, right? So,
Yeah.
since it's a dioic acid, I thought of finding the mass both dioic acid group will make. That was 90 because carbon is 12, oxygen is 16, hydrogen is 1, right? And then remaining that from 132, since 90 is made up of this dioic acid, the rest is for the CH2 groups, which is having a count, which is represented by N. That is what we have to find. So 42 will be equal to the CH2 times N. CH2 again is 12 and 2, 1 for hydrogen, so 14. And then that is simple algebraic expression. Solving that, we got 3. And the answer for N is 3. The dioic acid was CH3, sorry, COOH. CH2 thrice COOH. That was found. Now we were talking about some experimental things. So let's go back there and then discuss how to prepare a standard solution. So remember, every time you are given an unknown compound, as you said, we can think of mass spectrometry. That's a good idea. And if it is specifically titration, if it is an acid or a base, alkaline, we can think of titration. First thing to do is preparing a standard solution. That is, we have to weigh a known mass, okay? You can use the suitable apparatus to do that. It can be a beaker, or what do we normally use? If it is not a beaker, what do we normally use? A watch glass, right? A
Yeah.
watch glass is ideal. So let's replace this speaker with a watch glass. Why a watch glass is ideal, I'll let you know in the next step. That's ideal. Because you can wash the wall of the watch glass easily to make sure that nothing is left in the wall of the watch glass. Okay, this is your substance. And now they have, dissolved it at this point. You can either do this or you can use the watch glass here. Okay, transfer that into the volumetric flask using a funnel. And then once it is transferred, you can wash out the watch glass wall and the funnel's wall. Why do we do that? To make sure nothing is left in the wall of the funnel or the watch glass, right? Remember very well, before filling the water up to this, when the water is half or quarter way on the volumetric flask, use the stopper, close the volumetric flask, and turn it upside down twice or thrice. Why do we do that?
To like mix the solution.
Yes, to give a thorough mix, right? And then make up
Yeah.
to the volume, up to the mark using a volumetric pipette, right? And then use a stopper, shake it thrice or twice again. Shake it like here and here. Or you can still make it upside down, right then. So that's how you prepare a standard solution. Now in the standard solution, you have the known mass dissolved with the known volume. Now do the titration, but if you have made 100 centimeter cube over here or 250 centimeter cube over here, you don't have to use the entire, just withdraw a known portion, which is ideally 25 centimeter cube onto the volumetric, not the volumetric, but the titration flask. Titrate it against with the known base. The alkaline should be known by its concentration so that you can read the volume, so that you can find the amount. And using the balanced chemical equation, you can find the amount here. That will be the amount on 25 centimeter cube. Then you can compare that on 250. So you have found the amount on 250. By this point, you know the mass. Hence, you can find the molar mass. You know what is that missing part is. So if it
Yeah.
is not mass spectrometry, when it comes to titration, analytical technique, that is how we do it. All good, right?
Yeah.
Okay. Moving back to the paper. Assuming that the rest of the questions marked are done, not marked are done actually. That's an open question, a 6 marks one. Scary. Use the
Yeah.
student's result to calculate the delta H2 for the reaction 2 and determine the enthalpy change delta H1 in kilojoules per mole for the decomposition of magnesium carbonate using the energy cycle. Assume the specific heat capacity of the reaction mixture is same as water, so 4.12. You are not supposed to remember.